Welcome to the Spectral Geometry in the Clouds seminar. This week we have the pleasure of having Jonathan Rohleder from University of Stockholm, and he will speak about the new approach to the hotspots conjecture. The stage is yours.
Thank you so much. Thank you very much for inviting me to speak here. I feel very honored to be able to speak about my recent work here. Yeah, as you can see, this will be about the hotspots conjecture, and probably I should first recall what this actually is. So yeah, let me just read that out. So the hottest and coldest points, this is a conjecture in physical terms, the hottest and coldest points within a perfectly insulated body should converge to the boundary of the body for large times. This is something conjectured by Rauch in 1974, and probably maybe the first time in really published in written form in the monograph by Bernd Carvoll. And the question is, what does this mean mathematically at all? So it looks like something related to the heat equation. And we are talking about a perfectly insulated body. So in principle, we may model this body by some domain in RD, and we would like to look at the heat equation, and something to be perfectly insulated, that would probably mean within the heat equation that we look at Neumann boundary conditions, so that the flux through the surface is 0. So that means we are actually studying the problem du over dt is equal to the tan derivative of u is equal to the space Laplacian with Neumann boundary conditions. So delta n is just a Neumann Laplacian. And then together with some given initial heat distribution u0. It is clear that this can be solved formally by writing down an expansion in eigenfunctions and eigenvalues of the Neumann Laplacian, or writing down the semi-group that comes from the Neumann Laplacian. So formally, the solution to that problem is just e to the t times the Neumann Laplacian applied to the initial heat distribution u0. And then we could start expanding this into eigenvalues and eigenfunctions of the Neumann Laplacian. So if mu1, which is equal to 0, so I take the convention mu1 is a 0 eigenvalue, and then in mu2, mu3, and so on are the positive eigenvalues, assuming the domain is connected, and the corresponding orthonormal basis of eigenfunctions psi1, psi2, and so on. I could clearly develop this into a series, and I would see one constant term that is independent of t, but even independent of x in this case. And then I see terms e to the minus t mu2 times something depending on x, plus terms with like higher coefficients mu3 in the exponent. And we are talking about what happens to the solution as t goes to infinity. And as t goes to infinity, this is a constant term, and this term, though, is, if say mu2 is an eigenvalue of multiplicity 1, then this is the dominating term in the asymptotics. So basically, the shape of psi2, so the second eigenfunction, would somehow dominate the long time behavior of the corresponding solution. That means the problem can actually be translated into where is it true that the second eigenfunction psi2 of the Neumann Laplacian would take its maximum and minimum on the boundary of the domain, and now there are actually different versions of that conjecture. You could ask, does it take its maximum and minimum only on the boundary? Or you could ask, if the multiplicity is not 1, but if it is 2, is that true for every eigenfunction corresponding to the lowest positive eigenvalue? So this is somehow kind of an attempt to summarize all these versions. So if you take psi2, any eigenfunction of the normal Laplacian associated with mu2, then the conjecture would be that it achieves its maximum and minimum only on the boundary. And actually what I'm going to talk about mostly is here is the strongest version of the conjecture, namely, does every eigenfunction corresponding to the first positive eigenvalue achieve its maximum and minimum only on the boundary? Yeah, there are of course a few cases where you could just check this by computation, which could be like intervals, balls, rectangles, those triangles that you could compute explicitly, like isosceles right triangles or equilateral triangles. In all these cases, the conjecture is of course true, and let me I mean, it is clearly true for the case of if you just are in one dimension. Oh, sorry, that doesn't look very nice. If you are in one dimension on an interval, then clearly the eigenfunction is just of cosine type and would clearly take its maximum at one endpoint of the interval and its minimum on the other endpoint. If you have a rectangle, then the eigenfunction would look like this in one direction and being constant in the other direction. So you would have the same effect. And if you check like balls, if you check for isosceles right triangles and so on, in these explicit cases, the conjecture is actually true. There is one class of domains for which the conjecture is true, based on non-trivial, highly non-trivial arguments that I would like to point out. And this is actually this is due to a work by Attar and Birdsey, and they are talking about so-called lip domains. And what is a lip domain? A lip domain is actually a domain that lies in between the graphs of two functions. These functions should be Lipschitz functions, and they satisfy one important extra condition, namely they should have Lipschitz constant at most 1. So there should not be any. So if the domain is rotated like this, that you could write it between the graphs of two functions, then actually they should not grow faster than with derivative 1, so to say. So it could be something like this. So the main point is that these two functions have Lipschitz constant less or equal 1. And which in particular means that they must have they must have corners, at least at these two endpoints. The class of lip domains is actually one of the first for which the conjecture could be proven. One typical example of a lip domain would be an arbitrary obtuse triangle. So any obtuse triangle could be placed like this, basically approximately depending on what it is, it would look like something like this. Right. Yeah. So let me summarize a little bit the history of partial solution to the problem. So obtuse triangles and symmetric 2D domains were covered by Banuelos and Birdsey and by Jerison Nadirashvili for certain not necessarily convex domains with 2 axes of symmetry. Even before Birdsey and co-authors came up with the full class of lip domains. Most of these, I mean, most of the somehow non-trivial results are in 2 dimensions, one has to say. One of the most recent breakthroughs on the conjecture is actually the proof for all triangles, which somehow sounds like something that should not be too difficult, as triangles are kind of explicit domains, but of course one cannot compute things explicitly, and it is actually quite hard work what they did. So Judge and Mundell managed to do that. There are a few more results that I cannot cover here, but these are maybe some of the most striking results. It's interesting that, and also highly non-trivial, that the conjecture fails for domains that are not simply connected, so for domains with holes. And counterexamples were given by Birdsey and Bernard in the Annals, and this was a counterexample with several holes, and later on Birdsey showed that actually one can find counterexamples with just 1 hole. The question is still open for general convex, or in principle even simply connected domains. So it could still be true for all convex or even all simply connected domains. We don't know. There are a few other recent related results in that context, and also some numerical observations and numerical results. These are, amongst others, due to Steinerberger, and to the numerics is actually due to Kleefeld. One interesting recent thing is due to Steinerberger to study actually the optimal constant, or to bound the ratio between the maximum of the function on the whole domain and the maximum of the function on only on the boundary. Of course, one would like to show that this is 1, or yeah, that would be what one would like to get. Yeah. What one should point out that somehow most of the results are basically due to 2 different classes of techniques. So one of them, that actually amongst others, all the results that Birdsey was involved in are results based on probabilistic techniques. There's another class of results, like the work of Jerison and Nadirashvili, or the work by Judge and Mundell, that works by tracing critical points of eigenfunctions under perturbations of the domain. What I would like to suggest today is looking at it from a more variational point of view. So as in several of the existing approaches, it would be convenient if one could exclude critical points of a second eigenfunction of the Neumann Laplacian, because if there are no critical points in the interior of the domain, there are no local maxima and minima, and so there won't be any global either inside. The question is how to do that. And of course, one could study like partial or directional derivatives of psi2. And of course, one could, or one somehow natural hope would be, so the partial derivatives of psi2 would again solve the differential equation minus Laplacian of that partial derivative is equal to mu2 times that partial derivative. So one might hope that these functions are actually eigenfunctions of the Laplacian for some, in some sense, good boundary conditions, and one could, and that they would correspond to the lowest eigenvalue of that Laplacian, and one could, so that one could say something about their maxima and minima, or their zeros, or their critical, the zeros of that partial derivative by just using somehow standard techniques, standard variational techniques for lowest eigenfunctions or lowest eigenvalues of Laplacians. The problem is, of course, if you take a directional derivative of an eigenfunction, it is very difficult to control which boundary conditions it would actually satisfy. But yeah, the hope would in principle be that one finds some directional derivative that by variational techniques can be shown to be strictly positive inside the domain, as one knows it for the lowest eigenfunction of the Dirichlet Laplacian, for instance. So one would like to do some type of Courant type nodal arguments. This is of course difficult because the boundary conditions of the partial derivatives or the directional derivatives are highly unclear. And that was a point where I kind of had given up looking at that project like 2 or 3 years ago. But I continued looking at it every now and then. And at some point I realized things get actually better if one, instead of looking at directional derivatives, actually would look at the gradient itself. So the gradients themselves would actually turn out to be eigenfunctions of some operator that one could do something with. And the operator is actually the following, without going into details like regularity here, but it is a vector-valued negative Laplacian. And the corresponding boundary conditions are that the vector field is orthogonal to the normal vector on the boundary, almost everywhere on the boundary, and it should satisfy a condition which is like the vector. How should one say? The vector field is kind of curl-free on the boundary, whatever that means. And this operator would actually be quite useful for studying this problem. And why is this? So let me look here. So what you see is just once more the definition of this vector-valued Laplacian, which would be a self-adjoint operator in the vector-valued L2. And if I would now start with an eigenfunction of the Neumann Laplacian, actually corresponding to any non-zero eigenvalue. So if I would start with the Neumann Laplacian, so minus Neumann Laplacian psi is equal to mu times psi for some positive mu, and then actually always the function or the vector field u being the gradient of psi, it would be in the domain of this operator, because it is quite clear that it satisfies this condition, because this is just the Neumann boundary condition. So nu is just being nu orthogonal to the gradient of psi, which is clearly the case. And if I look at the other condition, then I actually see that so d1 u2 minus d2 u1 would actually be just d1, d2 psi minus d2, d1 psi, which is 0 not only on the boundary, but particular on the boundary. And of course, u would satisfy the differential equation. So AU is equal to mu u. So actually, if you take any eigenfunction of the Neumann Laplacian corresponding to a positive eigenvalue, then its gradient would be an eigenfunction of this operator. And even more, if you take any eigenfunction of the Dirichlet Laplacian, so minus Dirichlet Laplacian phi is equal to lambda phi, and you look at something that I would like to write with that symbol, so look like a perpendicular gradient, or I don't know what a good name for it is, by which I mean just minus d2 phi and d1 phi, so just a vector that is pointwise orthogonal to the gradient. Then actually, I claim that this vector field u would also belong to the domain of this operator, because then u scalar product with nu would actually be gradient perp phi times nu. But now by just looking at, so I mean, if I take something that is orthogonal to nu, that would be one of the tangential vectors in one of the directions, and this is actually the same as minus gradient phi times the tangential vector in positive direction, and but this is 0 because phi is a Dirichlet Laplacian eigenfunction, so it is constant along the boundary particularly. And on the other hand, if I look at d1 u2 minus d2 u1, then that would be minus, that would be plus d1 phi minus d2 minus d2, so that is plus d2 phi. So that is actually the Laplacian of phi, which is a multiple of phi, so it is 0 on the boundary. So this is minus lambda phi, and it is 0 on the boundary. So also this perpendicular gradients of arbitrary eigenfunctions of the Dirichlet Laplacian would actually be, they would also of course satisfy the differential equation. So they would also be eigenfunctions of this operator. And the interesting thing is even more, if I take, so this is what I just explained to you, if I take any eigenfunction of the Neumann Laplacian, the gradient will be an eigenfunction of the operator A. If I take any eigenfunction of the Dirichlet Laplacian, then the perpendicular gradient will be an eigenfunction of A. And even more, if I take an orthonormal basis of eigenfunctions of the Neumann Laplacian corresponding eigenfunctions of the Neumann Laplacian, and I take all these functions except for the constant one, then the normalized gradients will form an orthonormal basis in the subspace of the vector valued L2, namely in the space of gradients of H1 functions. This is rather easy to check. And the normalized perpendicular gradients of an orthonormal basis of eigenfunctions of the Dirichlet Laplacian would actually give an orthonormal basis of another subspace of the vector valued L2, namely of the perpendicular gradients of H01 functions. These two spaces, so the gradients of H1 functions and the perpendicular gradients of H10 functions, are actually orthogonal to each other. And they show up quite prominently in, I mean, like if for people who are working in like systems like Maxwell things or Stokes, these spaces are very common. And what is also very common is the so-called Helmholtz decomposition. And what I give here is a very special version of it, namely the version for simply connected domains. And for simply connected domains, actually, it turns out that the L2 space, the vector valued L2 space, decomposes orthogonally into the gradients of H1 functions on the one hand, and this perpendicular gradients of H10 functions on the other hand. But now we know actually that we can create an orthonormal basis of eigenfunctions of the operator A of this first space by taking gradients of Neumann eigenfunctions, and we can create an orthonormal basis of eigenfunctions of this space consisting of eigenfunctions of A constructed from the perpendicular gradients of Dirichlet Laplacian eigenfunctions. So that means in the simply connected case, actually the spectrum of A only consists of Dirichlet and Neumann Laplacian eigenvalues. So always assuming that omega is simply connected, the spectrum of A is all positive Neumann eigenvalues together with all eigenvalues of the Dirichlet Laplacian, and even the multiplicities are preserved. That means, especially if one looks at the smallest eigenvalue of this operator, then it is whatever is smallest here, so either the smallest positive eigenvalue of the Neumann Laplacian or the smallest eigenvalue of the Dirichlet Laplacian. But this is, of course, something that is very well known. This is a result due to Polya from 1952. The smallest positive eigenvalue mu2 of the Neumann Laplacian is always strictly below the first eigenvalue of the Dirichlet Laplacian. And that means that if omega is simply connected, so that we have this equality for the spectra, actually the smallest eigenvalue of this vector valued operator A is just mu2, the first positive eigenvalue of the Neumann Laplacian. That means we could get, by looking at the variational principle related to this vector valued operator, we could actually study also mu2, the smallest positive eigenvalue of the Neumann Laplacian. And this is given in this proposition here. So actually, if we take omega bounded simply connected and some regularity assumptions like piecewise smooth with convex corners only. So if there are corners, there must be corners. So interior angles less than pi. Then the first positive eigenvalue mu2 of the Neumann Laplacian is given by the minimum of the Rayleigh quotient one gets from the quadratic form corresponding to this vector valued operator A, of course. And the quadratic form can be computed. Its form domain consists of all vector fields in H1 component-wise, so that they are orthogonal to the normal vector on the boundary. The form itself turns out to look like this. So there is a usual term containing the squared gradients of the components. And there is an extra term containing the curvature of the boundary. So if the domain is piecewise smooth, then we do have a curvature at almost every point. And the curvature is taken, this is a signed curvature actually. So it is negative locally where the domain is convex. And so one actually has to minimize this expression. And of course, equality one would have independently if one actually has an eigenfunction, which would mean that u is a gradient of an eigenfunction for the Neumann Laplacian corresponding to mu2. Yeah, and now one would be tempted to just use the typical like Courant type techniques to see that one gets or that minimizers could be functions that are strictly positive or strictly negative inside the domain. So the question is, can we conclude that the components of the gradient of psi2 do not change sign? And what would we need to do? The usual technique is, I mean, for scalar functions or for the scalar Laplacian would be, I take the eigenfunction and I take, or the minimizer, and I take the modulus of it. So now we would take the modulus component-wise, and we wonder, is that a minimizer again? And if yes, then we could conclude something about non-sign changing property by using like a maximum principle for like for harmonic or subharmonic functions. The point is, and the crucial point here is in which cases is actually this vector field with the modulus contained in the form domain at all, so contained in the set space of functions that we are minimizing over. And somehow, if we think of a polygon like a triangle, if you look at the polygon like a triangle, then we could have different situations. If we could look at this green face, then the components of the normal vector pointing outwards have a different sign. The first component would be negative, the second component would be positive. And that would mean, since u is orthogonal to nu, that would mean that the components of u must have the same sign, both positive or both negative. And if I then take the modulus of both components, I could still satisfy this condition. So somehow the green face is somehow fine. The red face here is a face where both components of the outer unit normal vector where both components of this outer unit normal vector are positive. And I see some questions in the chat. I think the most urgent one is this kappa the mean curvature? So this is all two-dimensional, right? So kappa is just the usual scalar curvature. So if both components of the normal vector are positive, like here, then u being orthogonal to it means that u1 and u2 must have different signs. But that means if I take the modulus of both, this is not preserved anymore. So after taking the modulus, this will not be orthogonal to the normal on such a part of the boundary. And this basically tells us in which cases we can expect that both components of the gradient are non-sign changing. Namely, I'm trying to summarize this here. So what we've just seen is that the argument works if the domain, let me call that, faces two opposite quadrants. And that means I can rotate it in such a way that, for instance, all exterior normals belong to the closed second or the closed fourth quadrant. That would be the case, for instance, in this picture. So all the exterior normals, there are no exterior normals that point into the interior of the first or the third quadrant in this case. It took me quite a while to understand that this is actually exactly the same as lip domains. I mean, it is probably not very difficult to see that, but somehow there was some confusion about it, and I had some very helpful discussion with Sugata Monda about that until I actually realized that this is really exactly the same thing. That means what we get here is the following: if I have a bounded, simply connected domain piece by smooth boundary corners only those that are convex, and if we assume that omega is a Lip domain, that is, we have just this situation where we can rotate the domain. This is just a question of rotating a Lip domain in such a way that it satisfies this property, that it looks like this. And if we rotate it like this, which we can of course assume without the loss of generality, it doesn't matter how we rotate our domain, then one gets out of these Courant type arguments that mu2 is simple, except in the case that omega is actually a square. And the corresponding eigenfunction may be chosen such that both partial derivatives are positive in omega, except for the case of a rectangle where one of them is of course 0. That means in particular the hotspots conjecture holds, and one gets even something about the location of the hotspots. I will show you some example, but that actually means this is a re-proof of the statement of the result by Attar and Birdsey on Lip domains. Not, you could say, not more than that, but it is actually, I mean, it is an entirely different method, and I do believe that this method has kind of a very natural, has some very natural things that I will explain to you once more in a second.
Before going on, there's a question from, say, 4 minutes ago I missed in the chat, if you don't mind. So the expression for the operator that this operator A that you've expressed seems to look very similar to the square of a Dirac operator with some special boundary conditions. Is this a relationship that you've already seen and have explored, or it's not something that
no, this is nothing I actually explored. I mean, I think the boundary conditions are probably a bit unusual compared with like the Dirac operators that one usually would study, I suspect. But this is of course something interesting to look at. That is true. Thank you.
Yeah, and also just to clarify, the kappa in the formula for the variational formula for the eigenvalue is the mean curvature of the boundary, right?
Yeah, I mean, what is, yeah, I mean, we are still two-dimensional, so the boundary is just a curve, so it is just the usual curvature.
Yeah. All right. Thanks.
Thank you. Yeah, and I would like to point out that after my preprint appeared, also there's a new preprint by Judge and Mondal, who studied Lip domains that are polygons and studied in some depth the critical points of the corresponding first of the second Neumann eigenfunction. Let me nevertheless show you just a few examples of that. One could say old result, but if I take any such domain and rotate it in a way, and if I can rotate it in a way that actually the normals would point into would belong to the interior of the second or fourth quadrants, then actually the result saying that the partial derivatives along both directions are strictly positive in the domain would of course yield a monotonicity of the eigenfunction along curves going from here to there. So it would turn out that actually there's exactly one point where the domain, where the eigenfunction takes its minimum, and another where the eigenfunction takes its maximum. So that one has somehow unique coldest and hottest spots in the terminology of the hotspots conjecture, so to say. I would like to point out that this is actually the largest class of domains for which one may expect at all that psi2 may have maybe strictly increasing in two orthogonal directions, because the Neumann boundary condition, so that would actually mean that the functions or the partial derivatives would not change sign on the boundary. And of course, as soon as one is in such a situation as here, they necessarily have to change sign on the boundary somewhere, because here both components, the components have different sign, so the components of the gradient, while here the components of the gradient have the same sign. So what one actually could expect at most in more general situations is maybe that there is one direction in which the eigenfunction is strictly increasing, or in which the directional derivative is non-sign changing. I would like to point out once more one particular thing. What appears very naturally in this approach, I think, is the fact that the domain is simply connected, because it turns out, so it comes up in, if I may go back, it comes up exactly at the point where we look at the Helmholtz decomposition, because if the domain is not simply connected, there's always another component here, a third part, which is orthogonal to the others, of course, that consists of vector fields that are both divergence free and curl free, which is of course not present if the domain is simply connected. And if there is another part here, then the spectrum would no longer be just consist, or would no longer just consist of these parts, but there would be something more. And the other thing is, the variational principle itself does not have anything to do with lip domains or with the direction of the normals or anything. So the variational principle itself is true for all simply connected domains with sufficient boundary regularity. So one might still hope that one could use this variational principle and some additional ingredients that one needs to study minimizers of this to get even more about the hotspots conjecture. So to get some results for the hotspots conjecture for simply connected domains that are not necessarily lip domains. But that probably requires some deeper methods in the study of minimizers of such variational problems. And I'm very sorry, let me just interrupt for a second, because I'm just seeing that my computer is running out of electricity. I apologize. Let me, yes, and somehow this is a related question. For which domains could one maybe expect that at least one directional derivative can be chosen non-sign changing? If one, for instance, would look at an equilateral triangle, then the smallest eigenvalue would have multiplicity 2, the smallest positive eigenvalue, and there's would be like a symmetric and an antisymmetric eigenfunction. And for both of them, one would see that there is one directional derivative that is positive everywhere inside the domain, which of course would be sufficient to exclude critical points. I would like to, in the very last minutes, I would like to say a few words on the case where the domain is not simply connected. So let me recall that we are still looking at this operator. And I did already say that if the domain is not simply connected, then there is the Helmholtz decomposition is more involved. So there's a third part that is also orthogonal. I just forgot the ring. there's a third part being in the decomposition, and this third part consists of vector fields both being kernel and divergence free. In particular, the components of these vector fields would be harmonic functions, and that would actually mean that the spectrum of the operator A then would consist of the positive eigenvalues of the Neumann Laplacian, together with the eigenvalues of the Dirichlet Laplacian, together with an eigenvalue 0 of a certain multiplicity. And one can actually say something about the multiplicity. But in any case, there will always be a 0 eigenvalue. So looking at the variation in principle will somehow be a bit different, because one would to have make sure that one looks at test functions being orthogonal, or test vector fields being orthogonal to the fields in the space HC. So mu2 is not the smallest eigenvalue of A anymore. It would still be the smallest positive or non-trivial eigenvalue, and one might wonder if that might be used to understand a bit better what actually happens to the maxima and minima of second Neumann Laplacian eigenfunctions in the case of multiply connected domains, where one of course knows that they don't have to be on the boundary in general, but also this requires of course advanced techniques, and I'm not yet aware of how to actually do that, but this is something to be looked at in the future as well. Thank you for your attention.
Thank you very much for for your talk. Now we have time for a few questions. If you have any, you can either ask them in chat or just unmute yourself.
Hello.
Can I ask a question?
Yes, of course.
So you use the fact that if there are no critical points, then no critical points inside, then they have to be in the boundary. Is this so? This seems to be a stronger version of hotspots, right?
Sure, yeah.
Is it expected to hold? Do people expect that this stronger version hold for any simply connected domain, say? Any numerics about it?
I'm actually not entirely sure about that question. I cannot tell you a very good reason why one should expect it, at least. It's not clear to me whether one should really expect that. I would certainly expect that there is a larger class of domains, larger than just these lip domains, for which this is true, as it is, for instance, true for equilateral triangles. But I don't know a good argument that would, or a good intuition that would somehow make me suspect this. That's not clear to me.
Okay, and the related question is that should I phrase it? Yeah, this is similar. So another thing you said is, give me 1 second to formulate it. So you actually want to prove that this vector field doesn't have zeros, right? Which is not equivalent to saying that there is one direction that doesn't have zeros.
No, I see. Yeah, no, exactly. So I mean,
did I say something wrong? No.
No. So yeah. So one would be happy to see that one of the components doesn't have zeros, right? That would be of course.
Right, but it's not what you actually want, right?
That would be sufficient. If one of the components never gets 0, then of course you don't have critical points.
Right, but you actually want that the vector doesn't have zeros, right? So which is component doesn't have zeros is a stronger statement and vector doesn't have zeros.
Yeah. Right.
Was there any attempt to to do it with the vector directly without going to components?
I'm not sure how to. I mean, how would one look at that? I mean,
for example, going back to this comment on Dirac operators.
Yeah.
Right. For example, for Dirac operators, people study zeros. For example, there's like bound total zeros of the spinner in terms of things, right? So, like eigenspinners cannot have too many zeros depending on the number of eigenvalues.
Yeah.
Just as an analogy, like, I don't.
No, I mean that might be an interesting analogy. So maybe one could look into their methods and see whether that somehow it could be used here. That's an interesting point. Thank you.
Yeah, no, that's all.
Thanks.
I have a question, if I may, Alex. The operator you define, if you are in a general curved space, it will not correspond to gradient. Like, have you looked at this operator A in a geometric context other than the Euclidean one, for instance?
No, I haven't.
I'm just curious. I don't see any reason to do so. It's just a new operator,
Okay.
so it's exciting. I'm not.
Yeah. No, but I haven't tried.
Thanks.
Hello.
We before going to the next question, there's just a comment by Chris Judge in the chat saying that to answer Misha's question earlier, numerics seem to show that there are no critical points in the interior of any convex domain in the plane, for example. So at least, I mean, I guess that partially answers Misha's.
Yeah. That's an interesting comment. Thanks.
So I think we have someone else for a question right now.
Yeah, I think I joined a bit late. So I wanted to ask, what assumption on the domain are you making? Like, did you, is it just simply connected, or?
I mean, I do make some regularity assumptions. So mostly, let me go maybe here. So mostly I assume that that could be relaxed, but I mean, I assume that the boundary is piecewise smooth with the corners being convex, because what I actually need is, so if I take the gradients of eigenfunctions, I need them still to be in H1 component wise. So that basically means I need the eigenfunction itself to be H2. So I require typical things that make the eigenfunctions, or I mean, that make the eigenfunctions for sure H2.
Does it seem natural that the hot spots or cold spots move to the corners?
I mean, it's probably, I mean, they somehow, one would probably expect that they move away from each other, right? And this is somehow for the lip domains, these are kind of naturally the points that are somehow very far away from each other. Yeah. So in that sense, it is natural.
Okay. Yeah, and do they always have to be positioned like this way? Like actually, like, you know, they are kind of vertically, like, how do you say, opposite? Like V0 and V1, V0, at least in the figures that you have, do you expect them to be like these?
Yeah, I mean, one would somehow expect them to be as far away from each other as they somehow reasonably can, right?
Okay, fine. Yeah. Thank you.
Thank you for the question. Now we have Konstantin Bakashkin that wants to ask a question as well.
Yeah, thank you. But okay, but maybe it will be it's a bit, let's say, kind of very naive, but somehow in 2 dimensions, especially in these maximum questions, one would expect something related to the complex analysis, because what somehow the feeling is that the gradient is in part considered as a kind of, I don't know, holomorphic function with complex values, but somehow the complex analysis was not mentioned at all. I just wonder if, let's say, kind of for general culture, if there are some results which are originators, which are based on, let's say, on the techniques of the complex analysis.
So as far as I remember, not so much. I mean, of course, one would also be tempted. I mean, naively, one would maybe also be tempted to deform the domain by using conformal mappings or such techniques. But I'm not aware of some results that in that flavor that actually led to some things here.
Yeah, okay, but as I said, I'm just a bit curious, and was it somehow surprising that was because I didn't mention anything in this direction? So maybe it's, I mean, this is completely wrong way, but anyway.
I'm not saying that it's wrong. Just I didn't use anything like this.
No, I'm not saying that it's correct. But I mean, okay, thank you.
Thank you very much for the question. I think we now have Dima Jacobson who wants to ask something.
Do you think anything along those lines you can do in 3 or higher dimensions? Because you can also look at the gradient, right? And you can look at the vector valued Laplacian, and all the components would be so you can have in dimension n, right? You could have like a vector with n components and things like that.
Absolutely, yeah.
And, I don't know. I mean, there are these absolute and relative boundary conditions, but maybe it's too naive to expect things that work in 2 dimensions to kind of straightforwardly generalize to higher.
Yeah. So the part that certainly would work in higher dimensions is the minimum principle, so the variational principle, replacing the curvature by something appropriate, maybe the mean curvature, whatever. And so one just has to compute what that looks like. So the variational principle would certainly be fine, and the minimizers would still be the eigenfunctions of the gradients of normal Laplacian eigenfunctions for the second eigenvalue. The argument that I tried to explain here about somehow which signs the normal has on which parts and how that relates to the signs of the components of U. This is something that is unfortunately more tricky in higher dimensions, and I don't think that it will be a reasonable class of domains for which one still could conclude that that it works to take the modulus component-wise everywhere.
I see.
This is the main problem, the main issue.
Okay, thank you.
Thank you very much. Dima, do we have any other questions for the speaker today? Well, if not, let's thank Jonathan again. So thank you very much for this talk today.
Thank you.